first speaker will be Peter.
And he will talk about the experimental signatures of a toroidal mode in nickel 58.
So, good morning, everybody. This morning, I would like to talk about some elusive mode, which was predicted long ago, but so far there's no clear evidence, the so-called toroidal electric dipole mode. And the example I'm going to discuss is nickel 58, and partially I will show some things you already saw yesterday, because this was actually the starting point of the whole thing, which we didn't expect. That wasn't the plan, but it kind of fell into our lap. So I'll start by briefly reminding you of properties of fundamental electric dipole modes. We heard a lot about that yesterday already. Then I want to discuss the specific properties of the toroidal mode, which also explains where the difficulties are. Then briefly remind you of this combined analysis we did using high resolution data in proton, photon, and electron scattering in nickel 58. And then want to convince you that transverse electron scattering may be a signature for this toroidal mode. And then in the end, discuss possible next steps and possible ideas how to attack this problem of the toroidal E1 mode. Okay, so let me remind you of the fundamental electric dipole modes we discussed yesterday: the isovector mode, the giant dipole resonance. These figures are just some sketches of snapshots, if you want, of the current distributions. And the main thing I wanted to remind you is that the operator here goes like R times your spherical harmonics. And then we also discussed yesterday this isoscalar compressional mode. That's, of course, a bit more complicated than in the case of the monopole, because we all know that the fundamental isoscalar E1 motion is an unphysical mode. So you have a more complex current or velocity distribution with local maxima and minima inside the nucleus of the density. And the corresponding operator is of higher order, R cubed times your spherical harmonics times the gradient of the nuclear current. But then in these models, you also predict another mode, an isoscalar toroidal mode. So it's shown here. And it's called toroidal or vortex mode because you have these current distributions with vortices. And the corresponding operator is then R cubed times your spherical harmonics times the curl of the nuclear current. So this is a fundamental mode like the giant dipole resonance or the isoscalar dipole resonance. But as I will show, there's very little known about it. But let me briefly dwell upon the relevance of this mode. Actually, I mean, toroidal modes generally appear in a large variety of physics problems. In hydrodynamics, solid states, cosmology, almost all fields have some kind of this vortical modes. So in the case of this nuclear electric dipole mode, this looks similar to this so-called Hill spherical vortex ring, which you know from fluid dynamics. But actually, the motion corresponds to oscillations along these streamlines. And I think the relevance of having such a mode is that's a pure quantum phenomenon. So it clearly contradicts fluid dynamical pictures of giant resonances. In such a picture, you can't have such a resonance. And such a mode is actually predicted in Landau theory, and it's called the transverse zero-sum mode, and its existence indicates that nuclei can rather be described as an elastic medium. And actually, this is not the only transverse zero-sum mode. There are also modes of higher angular momentum. And for example, one example we studied years ago was the so-called orbital magnetic quadrupole twist mode. That's another one of these transverse zero-sum modes. And I showed a sketch of what microscopic calculations predict how the current distributions are there. So So you have an upper hemisphere where the current rotates in the one direction, and the lower hemisphere where it rotates in the other direction. But then you also have a node in the transition density. So in the interior, it goes the other way around. That's the kind of picture. And this orbital magnetic mode actually is not related to deformation. That also exists in spherical nuclei. Okay, there's also a connection to a thing we discussed heavily yesterday, the so-called Pygmy resonance or low energy dipole strengths, because you will see that energetically it overlaps with the region where we discuss that the Pygmy resonance appears. I mean, particularly the isoscalar part, because this is an isoscalar mode. And if you look at this picture, and if you think about that, this mode, I mean, the data we have are mainly from surface type reactions, you can kind of see that the current distribution in there schematically looks similar. And actually, if you do a QRPA calculation and look at the transition densities of this toroidal mode, this is shown for the example tin 120 here. So this is the typical picture of the transition density times r squared. It's actually averaged over the energy region between 7 and 11 MeV. But what I want to point out is this looks exactly like the pictures we've seen yesterday, where you have this peak of the neutron density on the surface, and it's basically isoscalar in the interior. So you have very similar transition densities. So actually, some of the people working in this field say what we call the Pygmy resonance is nothing but a signature of the toroidal E1 mode. At least, I mean, if there is an independent motion like neutron skin oscillation, at least they should be mixed. Okay, so despite the prediction about 60 years ago and considerable theoretical work, there's no clear experimental evidence for a toroidal E1 mode so far. And in a recent review, they concluded, unfortunately, theory and experiment have not yet come to robust proposals for unambiguous identification of intrinsic vortical electric modes. Such proposals should take into account both nuclear structure and reaction mechanisms, and thus may be involved. Okay, so what's the problem? Let's look a little bit at the predictions. So these are calculations using various Sturm forces. Here in the left side, you see the isovector response. In the right column, you see the toroidal response. And the red dashed spectra are actually the simple two quasar particle distribution without interaction, which already tells you that this mode is very fragmented already on the quasar particle level. So that is maybe the biggest problem. This mode overlaps in energy with the other modes, the isovector dipole mode and the isoscalar compressional mode. So wherever you look, you'll probably have strong mixing. And that's maybe the reason why it's hard to find experimental signatures. Now, if you turn on the interaction, then you see that for the isovector strengths, as we know, there's a push to high energies. It's a repulsive interaction. This forms the GDR. You look in the toroidal response, you see that it's even more fragmented over a broad range. But something I want to discuss now is that a part of the strength by the interaction is shifted to low energies. It's not very much, but this is what I want to focus on. So let's look at the energy region in a bit more detail. I'll get that away. Oops.
It will vanish.
Okay, sorry, I have to go back. This was too fast. So in this figure, I just show you the response, the toroidal response, the compressional response to the isoscalar compressional response, and the isovector response in the low energy regions. 6 to 11 MeV. And the case I study is nickel 58 because that's where we have interesting data. Okay, so and these are calculations with various models. The main difference here of relevance is that the effective mass changes. So this has a very high effective mass, basically 1, and then the effective mass goes down. And what you can see is that the strength, if you go down with effective mass, is less fragmented, so it becomes more collective, but also the average energy goes up. So excitation energy of the mode at low energies and collectivity depend on the effective mass. What you also see is that basically for all these states, you have some isovector response. So these states are not fully pure. I mean, they're not fully pure isoscalar, obviously. They still have some component which allows excitation of isovector strength. For the contribution of the compressional strengths, this is predicted to be very weak. We know because it's a higher order mode, a 3H bar omega mode, this isoscalar dipole strength is at very high excitation energies. Okay. So how do you identify the toroidal character in the calculations? Well, you look at the kind of plots I showed you in the beginning, current distributions or velocity distributions. And so this is a cut in an XZ plane. And the arrows show you the current distribution, and the length of the arrow is a measure of the magnitude of amplitude. And the same for the velocity. Okay, so you see again that they have this characteristic vortices here, which makes you call them toroidal or vortical modes. You look at the velocity, you see the same thing, except that you don't have, in the velocity, you don't have the constraint on the surface. So here it goes to 0 in the count because the nucleus is finite, but for the velocity, this doesn't count. So, and then you can look at for example, you can look at the curl. Now the curl points into the plane, and black dots mean into the plane and white dots mean out of the plane, the arrow points, and the size of the circle again is a measure of the magnitude. So you can see you have the typical curl you would expect from such a toroidal mode, and the gradient in the ideal case should be 0, and you see it's not, but it's much weaker in general. Okay, so this is the kind of signature where you theoretically can say, okay, this is a dominant toroidal excitation. Now, what about experimental signatures? One thing actually came briefly up yesterday already. When you study the isoscalar dipole strength distribution with alpha scattering, that's the method of choice, you see an interesting phenomenon. This is actually these data were shown yesterday already. So here's the main peak of the isoscalar dipole resonance, but you also have a low energy bump here. Sagawa-san showed that. But this has nothing to do with Pygmy resonance because we are at higher energies. Let's see here, this mode is 15, and it goes down to maybe 10 in lead. So that's way above what we discussed yesterday. And actually, it also appears in the lighter nucleus like nickel 58, as I show you here. You see this low energy bump. And actually, if you would assume that this is compressional mode, that this belongs to the isoscalar giant dipole resonance, and then determine the centroid, and from that determine the compressibility, you come up with something which is actually a conflict with what you extract from the monopole resonance. So people concluded, when I want to determine the centroid of the isoscalar dipole resonance, I have to leave this bump out. So it seems not to be compressional, and actually already 20 years ago, Dario and some people in the audience, Niels and Peter Ring, also were authors of this, interpreted this as a coupling of the compressional and the toroidal mode. Okay, recently, the group of people, there's a group of people who has intensively worked over the last maybe 10 years theoretically on this, including P.G. Reinhardt and Valentin Nesterenko. They suggested that maybe a better idea is to get back to what I showed you previously, that part of the strength is shifted down in energy, and these transitions are predicted to be rather pure. So they're not representing a major part of the strength, but they are rather pure toroidal excitations. And this is just showing that this is a general phenomenon, calculation for calcium 40, calcium 48, nickel 58. There are also calculations on heavier nuclei, and you always see the same thing. So this is, again, the isovector response, and this is the isoscalar response, toroidal and compressional, and you always see this low energy peak here, which appears, and that is said to be rather pure toroidal. And maybe that's what one should focus on to find some experimental evidence. And a case which has been studied in more detail was magnesium 24, where you have actually only a few low-lying E1 transitions. So experimentally, this is kind of easier because you can easily identify them, and they predict that one of them has this toroidal characters. The other are of other nature. There, of course, these light nuclei, you also have alpha clustering, but there's one of those transitions, according to their theoretical analysis, is toroidal. And what they suggest to look at is, as the best experimental signature, is transverse electron scattering. And I mean, this immediately makes some sense because, I mean, to identify this mode, you have to look at the current distributions, and transverse electron scattering is exactly what measures current distributions in nuclear excitations. So let me remind you about electron scattering, inclusive electron scattering. Your cross-section is your mod cross-section times, for electric transitions, a longitudinal form factor and some transverse form factor with some kinematics in there. So the ratio depends on the kinematics. And let's look at the predictions for this magnesium state, which they claim is toroidal in their calculations. It's not clear which one would this be experimentally. This has to be established. So this figure shows you calculated cross sections, electron scattering, once at a very forward angle and one at a very backward angle. And because of these peculiar kinematics, if you go to these very backward angles, then the transverse form factor or the transverse cross sections get large. Okay, and this is shown here. So in red, you see the Coulomb form factor or longitudinal form factor, which actually is here superimposed by the black one. So basically all the cross section is longitudinal, and you have a very weak transverse cross section shown here. If you go to the backward angle, it's just the other way around. I mean, almost all of the cross section is now transverse. So that's the way to do it. You have to go to backward angles and look at the transverse cross sections. And what they predict is that these are very large for electric dipole transitions. I mean, for typical electric dipole transitions. Okay, now I want to discuss the case of nickel 58, because in nickel 58 we have a unique set of data which allows us to test these predictions. On the one hand, there was a study, which is actually a pioneering study. We heard yesterday a lot about doing alpha alpha prime gamma to study the isoscalar dipole response in the low energy region. And the pioneering study of this was done in KBI in the early 90s. However, one must say at that time they used large volumes sodium iodide, so the resolution was rather poor. So we've seen that it's important to do that with germanium detectors to really do the state-by-state analysis to understand the structure. Okay, and on top of that, we have a set of high resolution data from proton scattering, photon scattering, and electron scattering, which we can analyze together. And this set of data is unique, I think, because all of these reactions are very selective to dipole. So the PP prime, as you learned yesterday from Isabel's talk, is you see the E1, but also the spin flip M1. So if you go to very forward angles, you're selective to the dipole. Photon scattering, of course, is very selective to dipole. And if you do it with polarized beams like Higgs provides, you get unique parity information. And the electron scattering experiment I want to discuss is a bit older. It goes back to Achim Richter's work. It was a study at low momentum transfer and backward angles. So then actually the idea was to study magnetic response, which of course is purely transverse. So basically they were looking for M1 and M2 transitions. So let's have a quick look at the data. These are the results of the alpha alpha prime gamma experiment. And I want to point out that the excitation energy scale here goes from right to left. So the lower figure is just the inclusive cross section. And this is the difference if you tag with this gamma decay to the ground state. And this is basically the isoscalar E1 response, which is dominated here by 3 peaks at 6, 8.3, and 9.4 MeV approximately. As I said, the resolution, of course, is limited here. You already saw that yesterday, but still I briefly want to remind you, we have very nice data from RCNP on nickel 58, forward angle spectra. The blue is the most forward angle. And then some other angles are shown. And basically in this low energy region, you see a lot of peaks which you can analyze. The details have been shown by Isabel, and you have this bump, which is the giant dipole resonance. So just let me flash that again. Isabel in her master thesis did an analysis state by state between about 5 and 13.3 MeV. In total, almost 150 transitions were analyzed due to the very good resolution of this experiment. And you can identify whether these are M1 or E1 transitions. And in general, we find that M1 is very well described by DWBA. This is kind of this angular distribution always looks alike for all these spin flip M1 transitions. And the thing is, they peak at 0 degree. That makes this close to 0 degree measurement selective. And then you have the electric dipole case, and that's a bit more involved. And the description is not always as good because I think of some limitations of what you have as theoretical input here. But what I want to point out is that you still experimentally have a rather clear signature. This is this pronounced peaking at 0 degree. And actually for the E1s, you typically find an even steeper decrease with angle. So you have some guidance. But then we were in the lucky situation to have on top of this the gamma prime data. There were older data, which were partially done with Bremsstrahlung, but partially also with polarized Bremsstrahlung. So then you also get parity information. But there's a whole set of new measurements up to the neutron threshold done at Higgs with this laser Compton backscattering method. I won't talk about it. I'm sure we'll hear more about it in some of the talks later in the workshop. I just want to remind you that this laser Compton backscattering process produces a 100% transversely polarized photon beam. And then it's very easy to determine the parity of the excited state or the multipolarity of the transition by simply measuring in plane of the polarization or vertical to it. Then that tells you what is M1 and what is E1. And this is just one example I took out of the vast literature that you can really determine that very well. So this figure and the upper figure shows you the photon spectrum used, which you got from the laser Compton backscattering. And this is looking in polarization plane, and this is transverse to polarization plane. And you can really assign this is M1, this is E1 for the states. And we used that information because we had many cases where maybe it wasn't 100% clear from just using the angular distribution PP prime, but with this information on top, it was quite clear what's E1 and what is M1. And then you get this figure on the dipole strength distribution from the two experiments. I don't want to discuss the details, but just say that in general, we find very good agreement of exciting the same states. But on the average, the strength in gamma gamma prime is lower, in particular when it comes to the high energies here. The reason is mainly that the proton threshold in nickel 58 is rather low. It's at 8 point something, 8.2 MeV. So above that channel, you have obviously significant branching into gamma P reactions. This is why the strength almost dies out up here. Okay, one thing I want to remark is that some of the strongest transitions you see in the spectrum, isovector strengths now, agree at least within energy with what you see in the isoscalar probe I showed you in the beginning, the alpha alpha prime gamma. So it seems that these states which were prominent in the isoscalar channel are also kind of prominent in the isovector channel. Okay, but now let's come to the electron scattering. This particular experiment, which we use, most of the data which were measured in this case were taken at about the same incident energy, 50 MeV, and we only use those in the further analysis to simplify things. The resolution of the experiment was very good, and that's crucial to really identify, do we see the same states? So it was 30 keV roughly. Now in these spatial kinematics, you vary the momentum transfer by changing the angle. So you have a fixed electron energy and you change the scattering angle where you measure. This means you change the ratio between longitudinal and transverse cross sections in this case. And if an increase of the cross section with angle towards the most backward angle, which was 165, was seen, that then this was taken in the analysis of this paper as a signature of a magnetic transition, because it was clear that at backward angles, transverse cross sections dominate. Now, I show this figure again, combining now with electron scattering. And let me show you this. So if you compare, do you see the same states in these experiments? We use a criterion here, comparing two sets of data. And since all of these have very good resolution, you are quite selective with that. And I just show you examples where we conclude we really see the same transitions, and these are M1 transitions in all the three analyses. Yeah? But we also see some cases where, according to the energy, we really do see the same states. Using the combined information from PP prime and gamma gamma prime, they're clearly E1. But in this analysis, they were said to be M1, but as I said, the argument at the time was increase with angle, so increasing large transverse cross-section means it's M1. So according to this analysis, there are a set of E1 transitions with large transverse cross-sections. And this was exactly the signature predicted for these toroidal modes. So let's look at this in a more detail. I could show you analysis of all of these. They look pretty much alike. So that's why I just picked two, which actually correspond to two of these cases, which were prominent. These were the states which were prominent in the isovector excitation and in the isoscalar excitation, probably. At least they overlap in energy. But I could show you the whole set, and they pretty much look alike. So I think that's sufficient. So you see the cross-section here as a function of a scattering angle calculated for this fixed energy of 50 MeV. And you have, of course, a longitudinal contribution, and it's not zero. So at forward angles, it actually dominates, but you have this large transverse contribution, which at the most backward angle clearly dominates the cross section. Same thing here, but the ratio between longitudinal and transverse can be different. Also, the cross sections can have slightly different form because the underlying form factors are not identical in all cases. Okay, now the big question is this really unique? So what we did then is we said, okay, what would this, in this kinematics, what would you expect for a typical transition of the giant dipole resonance? And we took from the theory the most strong excitations predicted, but now just assume it's at this low energy. I mean, we're just using the shape basically, because these calculations are normalized. They're not absolute calculations. So the blue shows you again the prediction of using the toroidal information from a toroidal state at low energies. Now the yellow curve is, if you assume this is a fraction of the isovector giant dipole resonance, and you can see that this looks very different, basically because the ratio between longitudinal and transverse is very different. Transverse part is much smaller in this case. And we did the same game using the strongest transition from the compression mode, which is shown in green here. And again, you cannot describe the data neither with the compression mode angular distributions nor with the giant dipole resonance angular distributions. So we conclude that this is indeed an experimental signature for toroidal excitations. Okay, let me summarize. I showed you a combined analysis of these high resolution proton, photon, and electron experiments on nickel 58. And we think they reveal candidates for the long-thought toroidal E1 mode. And the experimental signature, or the best experimental signature so far, is looking at the transverse form factors. And the signature are that these are large for an E1 transition, much larger than you would expect for isovector excitations or isoscalar compressional excitations. I showed you also that some of these toroidal candidates are strongly excited with the isoscalar probe in the alpha prime gamma data, and in general, using QRPA calculations with this Sturm interaction, which is actually the one with the large effective mass, can reproduce these features. Okay, fine. Now, what do next? I mean, if you want to really establish this mode and its properties, one case is not enough. I think we all agree to that. So first thing I would suggest is investigate other cases, because this should be a generic mode. It should be everywhere except maybe the lightest nuclei. So since it's experimentally easier, and since it's probably wise to, at the moment, to stick to nuclei which don't have significant neutron excess, so you're not, I mean, you don't have to discuss about the structure of the low energy E1 strengths in cases where you have large neutron excess. So let's stick to nuclei which are more N equals Z nuclei or close to that, like nickel 58. Nickel 58, there is no neutron skin. So I already discussed the predictions for magnesium 24. So this is a kind of obvious case to look at. And I think we try to do that. Another case which might be interesting is calcium 40. In calcium 40, it's well known that close to 7 MeV, there is a P1 transition, which is isoscalar. I mean, in calcium, you can determine the isospin of the excited state. So it's an isoscalar E1 transition. Experimentally, it's a bit difficult because there's a close by 2+ transition, and so you need good resolution in these experiments. You must separate them. But if you can do it, like shown in this figure, you can extract the form factor. And that was actually studied in great detail, also in Darmstadt, but with a focus on the longitudinal form factor shown here. Yeah? Because the fact that you have finite strengths is, and these isoscalar E1 transitions are actually forbidden, at least in the long wavelengths limit for an n equals z nucleus. So this was interpreted in terms of isospin mixing to understand the form factor and the finite transition strength for this state. But in this context, actually, I don't know if one can see it, there was also a few measurements at very backward angles, mainly used to try to do so-called Rosenblut separation of longitudinal and transverse form factors, which means you measure at the same momentum transfer with different longitudinal transverse ratios, and then you can separate them. So maybe these points are not enough, but one could do some extra measurements in these backward angles, and I think that might be a very nice case to look at. Okay, another thing, recently we have completed at the Stalinag a setup for EE prime gamma experiments. So this is just showing the figure. So you have this setup of gamma detectors. It's based on lanthanum bromide detectors, and this shows you, similar to what we've seen yesterday, the correlation between excitation energy and gamma energy measured, and you see these lines which correspond to the excitation of certain states and decay back to the ground state. But I don't want to, this was the original experiment was aiming at something different. I just want to say we have such a setup available, it's working, so we can use it for other experiments. And one thing which might be very interesting is the following. There's a theoretical predictions from what we've seen so far that, I mean, usually in inclusive electron scattering, you measure form factor squared. But in theory, you can also look at the sign of the form factor. You can calculate, it comes out. So for the toroidal mode, they actually find that it has a sign difference between the longitudinal and the transverse part. While if you look at, so these are cases, at least in the momentum transfer range that we are looking at typically in these experiments, it's always the case. Different sign, longitudinal and transverse part. If you look, for example, to the GDR type excitation, then they have the same sign. So this sign of the longitudinal versus transverse form factors is actually another signature maybe for the toroidal mode. And that's something you can measure with EE prime gamma. If you look at the EE prime gamma cross section, then you have your usual longitudinal and transverse parts, and then you have interference terms. And one of these interference terms is the interference between the longitudinal and the transverse form factor. And it has a unique dependence on the azimuthal angle in your setup. And that is, of course, sensitive to the sign. And actually, if you choose the right azimuthal angles, basically you do an experiment at +45 versus -45. All the other terms, if you subtract the two, all the other terms cancel. You're just left with this response. So even if the cross sections are small, I think it's quite easy, in brackets, to measure that sign. Okay, so that's something we will look into and consider to do. Well, then I started wondering, are there other signatures in the isoscalar and isovector probes we have available? This needs to be looked at systematically in theory, and then experiments need to be done. And just some remarks and thoughts, and then maybe you also have ideas. One thing I want to point out is if you look in nickel 58 and also some other lighter nuclei, which are typically N roughly equals Z, these candidates for the toroidal mode actually are strong in the isoscalar and in the isovector response, as I showed you for nickel 58. Like the picture, like in the pygmy resonance in neutron-rich nuclei. But as I said, now we are talking about nuclei where we have no neutron or very little neutron excess only. So it seems some kind of signature for these toroidal candidates that they're in the low energy part, they are strong in both isoscalar and isovector response. Then it's something we need some theory advice on. Is there really a difference if you do the experiments, the isoscalar experiment using PP prime versus alpha alpha prime, in the sense that you might be sensitive to different regions of the transition count? I'm not sure if this is good enough, but it's something one can look at. Another thing which came back to my mind is when we analyzed calcium 48 PP prime, there you have a well-known set of low energy electric dipole states measured by Andreas and the group back when he was still in Darmstadt. I think 4 or 5 transitions only. And we've seen all of these transitions in PP prime as well. And they had anomalous angular distributions. I couldn't find the data quickly, but I can dig them out. So I remember at the time we were wondering because they looked anomalous. So maybe there's some signature in these transitions, since, I mean, what we've seen from the original calculations I showed you, they are not very collective. So they still have quite some single particle character. And then we know that this can influence the form factors or angular distributions quite a lot. So maybe there's some signature, and I'm really open to any other ideas from the audience. But let me close by thanking my collaborators on this work, in particular Isabel, who did this wonderful analysis of the nickel data, and also Valentin, who did most of the theoretical calculations I showed you. Thank you very much.
So, okay, so there are some questions in the audience. Maybe I ask first to the people at home. Is there any question at home? Right. Okay.
You should take the microphone.
Yes.
Otherwise,
Is there any question at home? I'll try, otherwise I couldn't.
Okay. No, okay.
No, it doesn't. But I thought. Okay. So,
Panayota.
please, Panayota, go ahead.
Yes, yes, hello.
Hello.
Hello, you can hear me very good. Yeah, first I would like to ask, you just mentioned in PP prime in calcium 48.
Yes.
That there was something, 1 second.
What I said
Hello.
was,
so that there was something anomalous.
what I said is these,
yes.
okay, what I said is these angular distributions look not like what we typically see in this forward kinematics in the PP prime angular distributions for E1 transitions. I mean, normally they are dominated by Coulomb excitation, but then you also have, at some angle, you have an interference with the nuclear excitation, and depending on their ratio, this varies the angular distribution. But some of those angular distributions we saw for the low-lying E1 and calcium 48 could not be explained in this picture. Let me put it that way. And they were varying from state to state very strongly. So that was a very unusual thing. And I know we were wondering about it at the time, but then the student had to finish and it was kind of left over. didn't solve
So
the problem.
those data are like somewhere in the thesis? Or?
No, they're not published. I have to dig them out, but I will.
Okay. Okay. Yeah. Another thing. Could you go back to slide 24? Yes, that was very nice. So here you identify some states as E1 instead of M1, and that's between 8 and 10 MeV, let's say.
Yeah.
So that's near the particle threshold, right?
The proton threshold is low. The neutron threshold is very high in nickel. It's at 12 MeV.
Okay.
But these experiments are not sensitive to threshold.
Yes, this energy region, isn't it consistent with what had been found long ago? I mean, the analysis was different about toroidal modes in lead 208.
Oh, okay. I mean, what you're talking about is we did some photon scattering experiment on lead 208 about 20 years ago. There the mode was at 7 MeV roughly. And that was at the threshold, but I think that's coincidence. That was my guess. So I doubt that it's a threshold phenomenon.
No, yes, I didn't suggest that. Maybe the energy region is just a bit higher than that.
Okay,
right?
let me say that I would expect that if you extend the electron scattering to lower excitation energies, you would see more transitions. If you look at the isoscalar response I showed, it's simply that at the time the experiment, because it was very hard to scan large excitation energy range with the particular setup used, and the original experiment was focused on studying the spin flip M1 resonance. They estimated it should be somewhere between 8 and 15 MeV, and that's the region they studied. So unfortunately, we don't have the lower energy data at the moment.
Yes, that was my other point, that when you look at the isoscalar transitions, there is the strong one at around 6
yes,
MeV,
that should be there.
And now we should be careful that we don't mix up, different phenomena, because that state at 6 MeV or so, you also then have calcium 40, which has a similar state.
Yes.
At 7 MeV. Anyway, yeah, that would be, I was going to ask if there was any data similar to this at lower energies. There are not.
Unfortunately,
and it would be very, very interesting to look at them both in nickel 58 and then also compare with calcium 40 to see if there are similarities between the two. Okay, in one it was
agreed to. I think what you're suggesting makes some sense, is that there may be a particular low energy transition which is purest. That's maybe okay.
Yes, okay, thank you. Yeah, thank you.
Is that
Peter, coming back to this anomalous angle distributions, as I said yesterday already, I mean, PP prime always has spin flip included. Separate that certainly off by angle distributions. You have to have the polarization data or whatsoever.
Well, that's right.
There's also the tensor interaction involved in the spin channel.
Okay.
And
that's. I know PP prime is a dirty thing, but we are looking at PP prime at close to zero momentum transfer. That simplifies things. I mean, if you think about, let's say, the effective interactions like Love-Franey, you can see that the isoscalar central part absolutely dominates in these kinematics. So I agree, there may be a spin contribution, there may be a spin isospin contribution, but they are very weak in these kinematics, even for the E1.
Because you have the interference effects and the amplitudes add up coherently.
Okay.
That is also taking place in the proton scheduling. So
yeah.
Interference effect, and that, particularly if you move a bit away from.
No, I fully agree. I mean, this is not, and let's say, it wouldn't, in my eyes, be an independent signature. But if you have a theory which describes, for example, this electron scattering data. And the same theory can predict this kind of behavior in the proton scattering. It's some additional confirmation, I would say. That's something one has to look at. I mean, it was just something I remembered, and I was wondering on, can we support what we've seen with other kind of observables?
Question is then, does these calculations for PP prime, the reaction calculations, do they include also the spin components?
Yes, I mean, what we do always when the angular distribution shown for the multipole decomposition, they are calculated with DWBA 07 using Love-Franey effective interaction. That has all that in. So, and you put in RPA amplitudes for, I mean, in those cases, we took the most collective ones, but you can do the same for any state you predict in your model.
Sí. Yes. Yes, sorry. Is there an, okay.
Nice talk. As you quoted, there is a claim that this toroidal mode may be, or the other way around, the pigment resonance may be a toroidal mode. Now, I want to say that one thing. First of all, the toroidal mode is present also in the nucleus with N equals Z.
Yes.
While what is called by pigment resonance, it is not. So it is similar to the isoscalar response, which is present also in the N-Cosel nuclei. So it's always there, but is not the pigment, because the pigment, what we call pigment, is present only when you have a neutron excess. So there's one thing I think one should taken by. And then the other thing is that you show the transition density, which are similar to the pigment. But are these transition density for nuclei with N bigger than Z?
That was tin 120 I showed.
Tin 120, yeah. So it's with the 20 neutron more than. But it will be interesting to see the transition density for the nucleus N equals Z, which I suspect they are pure isoscalar.
No, they're not.
They're not?
They're
like that.
They're like that. They're always like that in all nuclei. That's
also in and the N equals Z.
That cited down there, they show calculations from calcium to heavy nuclei, and they all look alike. That does not depend on the N to Z ratio.
Oh, that's sounds very strange.
And I mean, what?
So there is the nuclei N
the,
equals Z. You have a contribution of the neutron all on the surface.
It's a peculiarity of this kind of excitation that it seems you always see some response in the isoscalar and the isovector channel for these low-lying transitions. That's what they calculate for these toroidal candidates. They also show the isovector and isoscalar response, and you see you always have some isovector strength, some isoscalar strengths.
Also with the N equals Z. Okay.
Yeah.
Thank you.
If you look at our calculations for the tin isotopes, then you see this phenomenon from tin 110 to tin 132.
Yeah. Yeah, right.
Yeah.
So that is
tin 100, or well, did we calculate tin 100? It's the same. So yes.
Well, if I may add something, if you see some transition which is experimentally that you know how to identify that isoscalar and isobector, and you are sure it's the same transition, then you are sure in the transition density you will see contribution only from one type of particle, because it's the only way to have a state which is at the same time isobector and isoscalar. Otherwise, it would be impossible. So something that picture makes sense. I don't know if it must be in the surface or not, but it makes sense. Yeah. Sorry, I think he was first.
Thank you. First of all, I really like this state-to-state comparison with the three experiments there. We really learned something from the like state-by-state comparison, which of course profits from the low level density in the light nucleus, but that's nice too. So my question, I have two questions. As we have just discussed, this toroidal mode seems to be more prominent in the n equals to z range, so to say.
Well,
or...
I wouldn't say it's dominant. It just, if you go to the heavy, I mean, the neutron-rich nuclei, you just don't know. I mean, it's as was just discussed, the prediction is you also see toroidal strength there, but then it's not clear. I mean, this is just it's not clear if this is the full explanation of what you see experimentally. So the idea is to rather avoid that, because it complicates the interpretation, and go to a case where you know that the no neutron skin effect is present.
I mean, we know there's a bunch of things going on there, yeah.
But in principle, of course, you can then, once you've identified the signatures, you might try to access these cases we discussed yesterday.
And coming from the experiments, you investigate the excitation, but could we learn something from the decay as well? Are there any predictions on how the toroidal mode is supposed to decay?
I think if you use hadronic probes like alpha prime gamma and pp prime gamma, there the gamma basically saves to pick out the E1 response, because otherwise you typically have other modes excited and you must first separate them, and then you get a lot of model dependency. So this is a very nice way to get E1 to excite only the states which are E1 excitations. If you do electron scattering, I showed you, yes, you get new observables, which might be interesting.
Thanks.
Yes. So the last question, and could you keep it not very long?
Sure. It's okay.
Reconnecting basically to the calcium isotopes, and you mentioning 48 calcium, and I was wondering that Panayota didn't comment on that. There's the work of her with Vera, right? Where they looked at the gamma gamma prime and the alpha alpha prime, and they saw this prominent isoscalar state. And they also looked at the velocity distributions there. And it was a very peculiar state that they identified in that region. So what would be the difference for that interpretation compared to saying, all right, you should have these toroidal states at these energies as well?
Okay, I think what you have to do in the various models is to calculate the electron scattering prediction, and then we can see how well or not well that describes the electron scattering data. I mean, that's the way to go, I think.
Yeah. I mean, the question would obviously be with Panayota's transition densities, putting that, for instance, in Eduardo's code, would you get these peculiar proton angular distributions?
Yeah, that is, I think for any model which thinks it makes decent predictions, yes, you can do that. And it's just, I don't know, it's just something which occurred to me when I prepared this talk. So yes. I didn't even find the data so quickly. I have to dig back in some of our backups to find that. Or I have to ask the student who's still around, who's now a member of our institute. So he certainly has it somewhere. So we can dig it out. It's just something which came back to me, that we were wondering at the time why they look so unusual and so different from state to state. So it's a speculation. I don't know if this is
okay. So I think we must move. So let's thank Peter again.